Okay.
Hello friends, welcome to the channel Physics by IITians. In this lecture, we shall revise the topic. This is a very important topic. The topic is special theory of relativity. I only discuss about the formulas and how to solve the related formulas, how to solve the problems related to that formulas in this video lecture. Okay, but I shall make another video series describing each and every uh, essence of the special theory of relativity, because this is a very good kind of physics here. So here we shall not discuss more about the theoretical details, but we shall know how we can solve this kind of problems related to special theory of relativity. We should know why do we need special theory of relativity. Okay, so suppose you are in a rocket and you have a clock, you have a scale in this rocket. Okay, so what will happen when you measure the things, and what will happen if I measure your scale, your pencil, your watch? So in front of according to my perspective, will it be the same, that is my clock? Will it be the same time that will show on your clock also? Also, the length I am measuring here from here, will it be same as you are measuring the length of your scale inside residing inside the rocket? So actually, whenever we are talking in terms of the velocity, in terms of the time, we don't know really if it changes when in a frame that is moving. So whenever we are inside the earth, whatever we are measuring, whether it is the length or it is the time, we know that if I measure it in India, or if I measure it in America, or if I measure it in Antarctica, or if I measure it in Australia, it will remain the same. Okay, so the time also, whether they decide that whether this is the day or night, but the time interval, basically delta t, that is the 1 minute time or 1 second time or 1 hour time, is everywhere is same inside the earth. But whenever we are talking that in terms of spaceship, or we are talking in a frame which is moving and moving with the speed comparable to the speed of light, then we have to counter, or we have to count for the special theory of relativity. Okay, so the special theory of relativity is the failure of the arises due to the failure of the Galilean transformation, and it is giving us the new kind of transformation, and that is also known as Lorentz transformation. And we shall see here time and space will act different in special relativity, and we will also know relativistic momentum, relativistic energy in special theory of relativity. So what is the Galileo's transformation? So Galilean transformation basically nothing but our everyday experience. Suppose two trains are moving, and they are they are moving forward to each other. So they are coming forward to each other. We usually add their velocities, and if they are like passing in the same direction, then we subtract the velocities. And here we don't know actually anything about the time relation of the time space, nothing. I mean, just we only consider these formulas like there is just two coordinate system, that is xyz, and another coordinate system, that is x prime y prime z prime, and they are inertial coordinates. So I shall tell you what are the inertial non-inertial coordinate means. But whenever if we are considering the transformation from a s prime coordinate to s coordinate, so we will use this formula, that is y is equals to y prime plus vt if the motion is along the y direction, and x is equals to x prime, y equals to y prime, and z equals to z prime, and t equals to t prime. So if the motion is along the x axis, then we shall consider x equals to x prime plus vt, and yz will become same as y prime z prime, and t will become t prime. So these are the Galilean transformation, and it can tell us that what happened in one frame, it can tell what can happen in the another frame of reference. Okay, so here look what we have already discussed here. So if we choose two reference frame S and S prime, and S prime is moving with a velocity of v, then we can write x prime equals to x minus vt, y prime equals to y, z prime equals to z, t prime equals to t. Now what will be the transformation of distance or length? That is, you measure the length of an object in the S frame or S prime frame, the distance between the two events will become delta x. And what will be the transformation of velocities? That is, I have already told you that u equals to u prime plus v, or u prime equals to u minus v, where u and u prime as measured by two observers in their frame of reference, and x1 t1 x2 t2 be the coordinates of initial final events in frame S, and x prime t1 prime x2 prime t2 prime be the coordinate of final and initial and final events in the S prime frame. So actually these are not important here, because I am going to tell you the most important formulas in special theory of relativity. So this is the most important thing in the special theory of relativity, that is the Lorentz transformation. Galilean transformation cannot tell you the effects of special in that is coming in special theory of relativity due to the motion of that object. So Lorentz transformation is going to give you the solution of this kind of spatial features whenever the object is moving comparable to the velocity of light. So the Lorentz transformation x prime equals to x minus vt divided by root over 1 minus v square by c square, where x prime, y prime, z prime, t prime is the coordinate frame system in S prime, and x, y, z, t, these are the coordinate system in reference frame S. So y prime will become y, z prime is equals to z, t prime equals to t minus vx divided by c square whole divided by root over 1 minus v square by c square. Now look here, the difference between the two formula here is with this here, that is x and t. So x prime, there is another factor, that is divided by root over 1 minus v square by c square term, and t prime, this is t minus vx by c divided by root over 1 minus v square by c square. Vx by c square divided by root over 1 minus v square by c square. So these terms here, x and t, these are the main, it will play the main role in the special theory of relativity. And if you take the inverse Lorentz transformation, that is from x prime coordinate to x coordinate, or s prime frame to s frame, then you have to apply this two formula. For x equals to x prime plus vt prime by root over 1 minus v square by c square, and t equals to t prime plus vx prime by c square divided by root over 1 minus v square by c square. And gamma equals to here, that is root over 1 by root over 1 minus v square by c square is gamma. So v is always less than c, because if v equals to c, this factor will be infinite. So this v, the most maximum limit of v is c. So if v is near equals to c, then let me adjust it. This is going somewhere. Yes. If v is equals to c, then gamma will be 1. So length contraction, that is the here this I shall tell you the formulas for the length contraction. So the formula for the length contraction, that is, if the proper length of the rod, suppose you are taking a rod, okay, and the rod length is measured in the S frame and S prime frame, where S prime frame is moving with a velocity of v, that is constant velocity. So inertial frame, that is the frame is moving with constant velocity, and non-inertial frame, that is a frame that is moving with varying velocity, that is having acceleration or deceleration. So here in special theory of relativity, we shall only tell the constant the velocity reference frame, that is inertial reference frame. So if we measure the length of a rod, and in the S frame the length of the rod is L0, that is x2 minus x1, and in the S prime frame the length of the rod is L prime, that is x2 prime minus x1 prime. So, or if we write it as L naught for the S frame and L for the S prime frame, then actually is the L equals to L prime L naught? It is not in case of special theory of relativity. Earlier I have given you the example that if you measure a rod of length L or L naught, whether you are measuring in India, whether you are measuring in America, it will be same, that is L naught. But in case of special theory of relativity, the frame of reference, that is, or suppose I am giving another example, that if you are measuring a length in staying at home, or if you are measuring that particular length of the same object staying inside a train that is moving, but the length of the rod will become same, because the train velocity is not comparable to the velocity of light. But suppose you are going through a train, you are staying within a train that is moving the velocity comparable to light, then you are measuring that rod which you have measured when you were at a rest position. So the length of the rod will become changed. And what is the relation, that how much change you will get, that is L naught, if it is proper length of the rod, then L naught equals to L divided by root over 1 minus v square by c square. So this factor, so due to this factor, the L naught is not equals to L, and you get a contraction, that is the length of the rod will seem it is contracted. Now if we measure the time, so why I am telling you the time? Because actually in our perspective, time is just like not relative. Time is fixed. That is past, future is future, present is present. We can go to the past, we can't go to the future, but we can only live in the present. But special theory of relativity is not giving you this same conclusion, because present, past, future, everything is just illusion of time. In special theory of relativity, one person can go to the past, can go to the future. So the Doraemon, real life Doraemon, that is the time travel machine, can be actually possible in the theory of special theory of relativity. Okay. So suppose you are staying at home, and with a rest position you are measuring the time, that is, so suppose your rest clock, the time interval is giving as delta t equals to t2 minus t1. Now suppose you are within a train, and the train is going with the speed comparable to the light, and the time you have measured for in your clock, that is delta t prime, and the interval delta t prime is t2 prime minus t1 prime. Now in the Galilean consideration, the delta t, that is the time interval, will be same for both the cases. But in the special theory of relativity consideration, the time interval in the two different reference frames are different, and delta t is not equals to delta t prime, but delta t equals to gamma into delta t prime. Okay, so here look here, this gamma factor, due to earlier that L naught equals to L by root over 1 minus v square by c square, now it is delta t equals to gamma delta t prime, or gamma delta t prime by root over 1 minus v square by c square. So here, as this gamma factor is greater than 1, or maximum it can be equal to 1 when v equals to c. So if, since this factor gamma is greater than 1, so delta t must be greater than delta t prime. Okay, so time is actually dilated. Velocity addition theorem. So this is another beautiful theorem here. So here what you have to consider, suppose you are in a two reference frame considering s and s prime, and moving object with different velocities. Okay, so two objects are moving with different velocities, and they can come to each other, or they can away from each other, go away from each other. So you have to apply the velocity addition theorem. Now, if you consider that the two objects are going to the same direction, so what will be the speed of those two, that is the addition theorem? It will give you, for the Galilean consideration, that is ux prime, if we consider that ux prime should be just only u minus v, considering ux and v are the velocities of these different objects. Okay, but here in special theory of relativity, there another term will come, and that is ux minus v divided by 1 minus uxv divided by c square. Now if these two objects are coming to each other or approaching to each other, then this ux plus v divided by 1 minus uxv by c square. So this kind of modification in the term here due to the special theory of relativity. Okay, so we have learned here the length contraction formula, that is ls prime is ls root over 1 minus v square by c square, and ls prime is the s prime frame, ls is the s frame. So if this is the length, that is the stationary length, and this is the moving length, as such the moving length has been contracted. Okay, suppose this is a another time dilation example. So this is a stationary clock. So look here, the time here is around 12:20. So suppose this is a moving clock. So and the moving clock is moving with the speed 87% speed of light, and time here is 12:10. So as per that, this time is dilated. Okay, so if I want to tell you that you just think that you are going with the velocity of light, and think about how the world, how the buildings, how the objects will appear in front of you. Okay, think about that. So this formulas we have already seen here. So if that similarly, if you take uy prime, we will get dy dt by gamma 1 minus v by c square dx dt, and uz prime equals to uz by gamma into 1 minus v uz by c square. Now if we take the equivalence of mass energy, that is mass and energy both are equivalent, they are not actually very much different from each other. We can convert mass into energy, and we can convert energy into mass. Okay, so everything is possible with this formula, that is E equals to mc square or Ek equals to delta mc square. So please remember these formulas, that is the velocity addition theorem. When the relative velocity of s prime is along the x-axis of s, that is the speed of light. Okay, so what will be the relativistic mass? Relativistic mass mv equals to gamma into m naught, where gamma is root over 1 minus v square by c square, and m naught is its rest mass. And this is m by m naught versus v by c graph. So whenever v is near equals to c, or v is exactly equals to c, then m will become infinite. So we cannot construct a spaceship that is going with the velocity of light, because the mass of that spaceship will become infinite. Means it will be very heavy. What will be the relativistic momentum? Relativistic momentum is P equals to mv, that is m naught v divided by root over 1 minus v square by c square. The relativistic force is F equals to dp dt, that is ddt of m naught v divided by 1 minus v square by c square. Relativistic work, that is delta W equals to F delta S, that is m naught gamma cube v delta V. Relativistic energy, so this important, that is E kinetic equals to m naught c square into 1 by root over 1 minus v square by c square minus 1. Non-relativistic case, so whenever we consider the non-relativistic case, we get the kinetic energy as half m naught v square, and it can be derived from the relativistic calculation. Okay, and the mass energy equivalence relation is E equals to mc square with a velocity dependent mass, that is mass equals to m naught into gamma, where gamma equals to root over 1 by root over v square minus c square. Okay, the body, now the here this is, please remember this formula. I think you all know this formula, that is energy momentum relationship, that is A square equals to P square C square plus m naught square C to the power 4. For photon, E equals to Pc, because m naught is 0 for the photon. Okay, so these are the formulas that you should always remember for the time dilation, for the length contraction, for the relativistic energy, for the relativistic momentum. Please note down these formulas. I am giving you this not zoomed. Let me zoom it, okay, so that you clearly view. So please understand these formulas and note down these formulas. These are the main important formulas for today's class. Now we shall solve some problems. So let's take an example. The period of a pendulum is measured to be 3.0 second in the reference frame of pendulum. What is the period when measured by an observer moving at a speed of 0.95 c relative to the pendulum? So instead of the observer moving at 0.95 c, we can take the equivalent point of view. The observer is at rest and the pendulum is moving at 0.95 c past the stationary observer. Hence the pendulum is an example of a moving clock. Okay, so the proper time, that is 3.0 second, that is can be written as delta Tp. So now the clock is moving and the moving clock will run more slowly than the stationary clock by a factor of delta T equals to gamma into delta Tp. So delta T will become 1 by gamma, that is 1 by root over 1 minus v square by c square. So v square will become 0.95 c as the speed of that pendulum. So 1 by root over 1 minus 0.95 c whole square divided by c square into delta Tp. So just put the formulas and put the values, you will get 9.6 seconds. So the moving pendulum takes longer to complete a period than a pendulum at rest does. In the next video, when I will tell you each and everything, I shall give you the visual demonstration also, that how do you visualize these things. So let's take another example. Suppose you are driving your car on a business trip and are traveling at 30 meters per second. Your boss, who is waiting at your destination, expects the trip to take 5 hours. When you arrive late, your excuse is that your car clock registered the passage of 5 hours, but that you were driving first and so your clock ran more slowly than your boss clock. So if your car clock actually did indicate a 5-hour trip, how much time passed on your boss clock, which was at rest on the earth? So the gamma factor first you have to calculate, that is 1 by root over 1 minus v square by c square. So here v is 3 into 10 to the power 1 meter per second and c is 3 into 10 to the power 8 meter per second. So 1 by root over 1 minus v square by c square will give you 1 by root over 1 minus 10 to the power minus 14. So just binomial expand this, okay, and you will get that this del gamma, that is factor of gamma, is this much. So delta T, that is gamma into delta Tp, and it will become, so delta Tp is the 5-hour duration into gamma, that is 1 plus 5.0 into 10 to the power minus 15. This is actually equal sign. Okay, these are all equal sign. So the value of gamma is this much and delta Tp, that actually the time duration is 5.0. So it is 5.0 hour plus 0.09 nanosecond. So look here, if you are going with this 95% speed of light, you will get this amount of time dilation for the 5-hour dilation. So look, this amount is much less. But if you approaching 0.98 c, if you approaching 0.99 c, you will get a huge time difference will happen actually. Okay. So let us take another example. A spaceship is measured to be 120.0 meter long and 20.0 meter in diameter while at rest relative to an observer. If this spaceship now flies by the observer with a speed of 0.99 c, what length and diameter does the observer measure? So what you have to apply? You have to apply the length contraction formula. So L equals to LP into root over 1 minus V square by C square. So LP is 120 meter and V is 0.99 C. So put here 120.0 meter into root over 1 minus 0.99 C square by C square. So it will give you 17 meter. So the diameter measured by the observer. Now what is the length? The length is 70 meter. And another question is the diameter. You have to, what will the observer measure? The diameter measured by the observer is still 20.0 meter, because the diameter is a dimension that is perpendicular to the motion of length contraction motion, and the length contraction occurs only along the direction of motion. So whenever you are measuring perpendicular to the direction of motion, the length will be same. It will not change. So the length will be contracted only along the direction of motion. So here we have an announcement that you can prepare for exam, and you can analyze your preparation through our timer based online test series, and detailed solutions and question solving tricks are also provided. After each test you will get full PDF solution, and you can ask any question if you have any doubt. Only you have to pay 249 for 5 tests, and those are full length tests. Subjective test 549, both tests are only 699. So these are the payment and registration link. It is already given in the description box also, and we have interview guidance series also. And please contact us on our Telegram channel Physics by IITians, and contact us individually on Telegram for more information. So let us take another example. The two spaceships A and B, they are moving in opposite direction. An observer on the Earth measures the speed of the spaceship A to be 0.750 c and the speed of the spaceship B to be 0.850 c. Now find the velocity of spaceship B as observed by the crew on spaceship A. Okay, so you are measuring the speeds on spaceship B and A as 0.850 and 0.750, but what will be the velocity of the spaceship B if someone on spaceship A measure? So we can solve this problem by the velocity addition theorem. So we can solve the taking S prime frame as being attached to the spaceship A. So A is moving in a reference frame. We attach it the S prime frame. So the relative to the Earth, that is Earth, our Earth is the S frame. So we can consider the spaceship B as moving with a velocity that is relative to Earth. So hence we can obtain the velocity of spaceship relative to spaceship A by the velocity addition theorem. And what will be that? If we consider the spaceship velocity Ux prime, that is related to S prime frame, and S prime frame is A frame or the attached to the A observer. So Ux prime is Ux minus V divided by 1 minus Uxv by c square. So put this values, that is Ux equals to 8.850 C and V equals to 0.75 C, and put this one and you will get minus 0.977 C. So here this is along x direction, and you have to write the according symbol signs also. Okay, whether it is along the positive x direction or whether it is along the negative x direction, you also consider that here. Okay, so I think you understand. Now let us consider the next example. Imagine a motorcycle moving with a speed 0.80 c past a stationary observer. If the rider tosses a ball in the forward direction with a speed of 0.70 c related to himself, what is the speed of the ball relative to the stationary observer? So first understand this question, that someone that is moving in a motorcycle and the speed of the motorcycle is 0.80. Okay, and it is respect to a stationary observer which is standing still. Now if the rider tosses a ball, now he is moving and he is tossing a ball, and the ball is going in the forward direction, and the speed of that ball is 0.70 c relative to himself, that is the motorbiker. So what is the speed of the ball relative to the stationary observer? So this will be solved by the velocity addition theorem. So the speed of the motorcycle relative to the stationary observer, that is V, is 0.8 c. The speed of the ball in the frame of reference of the motorcyclist is Ux prime because the motorcycle frame we take as S prime frame. So the ball velocity with respect to S prime frame is ux prime. So it is 0.7 c. You have to find the ux because you have to find the ball relative to your or relative to the stationary observer. Suppose you are the stationary observer. So you have to find what is the velocity of the ball relative to your frame of reference. And now let us take your frame of reference is S and the velocity of the ball with your frame of reference is ux. So ux equals to ux prime plus v divided by 1 plus ux prime v by c square. So ux prime is 0.7 c, v is 0.80 c and divided by 1 plus 0.70 c into 0.80 c divided by c square. That is 0.96. Okay. So here this is another example, another kind of question, that is the relativistic momentum. An electron which has a mass of 9.11 into 10 to the power minus 31 kg moves with the speed that is 0.750 c, finds its relativistic momentum. So mass has been given and u, that is the speed of already given. So p equals to mu by root over 1 minus u square by c square. me you have to put 9.11 into 10 to the power minus 31 kg. U is 0.750 into 3 into 10 to the power 8 meter per second divided by root over 1 minus u square by c square. You will get 3.1 into 10 to the power minus 22 kg per meter. Okay. So here also there's another example. An electron in a television picture tube typically moves with the speed. Find its total energy and kinetic energy in electron volt. So the rest energy of the electron is 0.511 MeV. You should remember it. That is rest energy of electron is 0.511 MeV. So E equals to mc square divided by 2 over 1 minus u square by c square, where mec square, this is the rest mass energy. So 0.511 MeV divided by root over 1 minus u is 0.250, that is the speed of the electron inside the television picture. So put this value of u, that is 0.250 c divided by c whole square. It will become 0.528 MeV. So this is 3% greater than the rest energy. So the kinetic energy will become E minus mec square, that is the energy minus the rest mass energy. So the energy of E is 0.528 MeV and rest mass energy is 0.511 MeV, so 0.017 MeV. Okay, this is the energy. Another question, this just simple problems, you have to only put some formulas and you will get the values. That's all. Don't worry about the questions. These questions are really very much easy. Okay. So what you need here, you need to do here, you need to understand that when I should take the plus sign in case of velocity addition theorem, when I should take the plus sign, when I should take the minus sign in the velocity. So you have to consider, suppose the reference is moving along the positive x direction, you should take the velocity as positive. The reference or the particle is moving, or object is moving with respect to the negative x direction, then you have to take the velocity as negative of that, because these are all vectors. Okay. Here this question is, find the rest energy of a proton in electron volt. And if the total energy of a proton is 3 times its rest energy, with what speed the proton is moving. And determine the kinetic energy of the proton in electron volt. What is the proton's momentum? So first of all, the rest energy of the proton, that is E rest or ER equals to mp into c square, where mp is the mass of the proton, that is 1.67 into 10 to the power minus 27 kg into c square, that is 3.00 into 10 to the power 8 meter per second whole square. So it will give you 938 MeV. Now if you take the total energy of the proton is 3 times its rest energy, that is E equals to 3 into mpc square, then it will become the U will become root over 3 by 8c. Okay. So now what will be the kinetic energy of the proton? Kinetic energy of the proton is total energy minus the rest mass energy. So total energy here 3 mpc square minus mpc square, that is 2 mpc square. So kinetic energy is 1880 MeV. And what will be the momentum? That is the proton's momentum, that is E square equals to P square C square plus M naught square C to the power 4, or M naught here MP, so MP square C to the power 4. So it will become 3 mpc square whole square, that is P equals to 2650 MeV by C. Okay. So this, I think you understand how do you solve this kind of questions. In the next video, we shall learn about the light cone. This is a very important thing, and this is a very beautiful thing in special relativity. The space and time, these are all will form this kind of structure, the four-dimensional space and time actually. Okay. And in the next video, we shall learn about the Doppler's effect, and we shall learn this kind of questions that has already come in NET GATE paper. Okay. So thank you for watching this video. Join our test series to evaluate your performance. That is, this link has been already given in the description box. Please like this video, share with your friends, and subscribe our channel, and join our telegram channel for daily quiz updates and research articles and research guidance. Thank you so much.